got another problem on the board, this time with a function of 3 variables. So we want to find the location and value of the absolute max and min of this function, x squared plus y squared minus c squared, on the solid unit sphere. That's the set of points in 3 space where x squared plus y squared plus z squared is less than or equal to 1. Now again, because this is less than or equal to, we're not just looking at the level curve. The surface of the sphere would be the boundary of this region. That's a level curve for this function, which I'll call g of x, y, z. And I can use Lagrange multipliers there. But the points where I've got an inequality would be on the interior of the sphere. And so I've got to then check critical points that could be on the interior of that. Okay. Now, in this case, notice the function I'm trying to optimize is continuous. The solid unit sphere is closed and bounded. Extreme value theorem guarantees that there exists a max and a min. Okay. Sometimes that's going to be the case. In the homework, you'll see that you're generally told at the start of the problem set, all of these problems have a max and a min. Now, sometimes that's going to be from the extreme value theorem. Sometimes you're just being given that, because without the extreme value theorem, you might not otherwise know. Okay, so I'm going to now say I need to list all of the possible locations for my maxes and mins, and that will include critical points. Most of the examples that I'm working through in these videos are going to be regions like this that are described by an inequality, so that you have to check both critical points and boundary points. So that's combining some of what we learned from section 14.7 with the method of Lagrange multipliers, which we'll use on the boundary. If the boundary was a level curve, I might have the option of parametrizing it. Here, the boundary is a level surface. We're going to have to use Lagrange multipliers when we've got a function of 3 variables. I tend to do this just because you don't get a lot of examples like this in the textbook, so I want to make sure that you've seen them. In the textbook, you'd probably just have the surface of the sphere, so you'd just be doing this part of the problem. Just want to remind you to check, if your region is described by an inequality, you also have to check critical points. Okay. All right, so I usually check critical points first, because sometimes that allows me, as I'm working through my cases, to conclude that, oh, any points that I get from this case are already on my list. So if I look for the gradient of f, that would be 2x, 2y, negative 2z. That is always defined, so all my critical points will be where it's 0. The gradient of f will equal 0, means that 2x equals 0, and 2y equals 0, and negative 2z equals 0. So basically, all 3 variables have to be 0. I have a critical point at the origin, and that is included in that solid unit sphere. Excellent. Okay. So then on the boundary, I'm working with just the surface of the sphere. So on the boundary, more looking at x squared plus y squared plus z squared equals 1. And again, I've called that g of x, y, z. Now, the gradient of g is just going to be 2x, 2y, 2z. Okay, so we are looking for places where the gradient of f is a multiple of the gradient of g. So if the gradient of f is lambda times the gradient of g, that's going to mean 2x, 2y, negative 2z is equal to lambda times 2x, 2y, 2z. Which, of course, if I do the scalar multiplication, it's just lambda 2x, lambda 2y, lambda 2z. Okay, so let's get our system of equations. I'm just going to number them. First equation, first components have to be equal. So 2x is equal to lambda times 2x. Second equation, second components have to be equal. So 2y is equal to lambda times 2y. Third equation, third components have to be equal. So negative 2z is equal to lambda times 2z. And then the fourth equation is my constraint. And it is the constraint equation, x squared plus y squared plus z squared equals 1. I sometimes see people try to put the inequality here. We're trying to solve a system of equations. The Lagrange multipliers only works on this boundary surface. It does not apply for the points on the inside. That's why I checked for critical points separately in case there were any critical points on the inside. Might as well write. If I plug that into my function, I will get 0. Okay, so now I want to solve this system of equations. So my overall strategy is there's a lambda in the first 3 equations. I would like to try to solve for lambda in each of those equations so that I can make the brilliant observation that lambda is equal to lambda, which is equal to lambda. And then that should give me a relationship between x, y, and z, and I can plug that into the constraint. Okay. But if I wanted to solve for lambda in this first equation, it would involve dividing by x's. Something could go wrong. That's case 1. Case 1, what if x is equal to 0? So if x is equal to 0, notice equation 1 becomes 0 equals 0. So equation 1 is true. Now, I need the rest of my equations to be true, and unfortunately, plugging in 0 for x doesn't help me at all in equations 2 and 3, and only helps me a little bit in equation 4. So I'm going to move on to equation 2, but I'm going to now have 2 subcases here. So equation, let's do subcase 1a, okay, where y is also equal to 0, because that's what would prevent me from solving for lambda in this particular case. Okay, so if y is 0, then equation 2 becomes 0 equals 0, and so that equation is true. Okay. Now I'm going to jump to equation 4, because once I know an x and a y, I'll be able to solve for z. Okay, so 0 squared plus 0 squared plus z squared equals 1. Z is plus or minus 1. Okay. Now, if I stop here, I have not proved that I have found a point. Because how many equations did I look at? I looked at equation 1, I looked at equation 2, I looked at equation 4. Finding a solution to 3 out of 4 equations is not finding a solution to this system of equations. I have to look at equation 3 and verify that it will have a solution. Okay. So if I then look at equation 3, if z is 1, this becomes negative 2 equals 2 lambda. Lambda would equal negative 1. Okay. If z is equal to negative 1, this becomes 2 equals negative 2 times lambda. Well, lambda would again be negative 1. So there is a solution. Okay. Don't just do that as a mental check, because I've seen lots of students who get to the point where they have an x, y, and a z, and they say, I found a point, yay. And they've checked 2 out of 4 equations. That you have to be able to satisfy all 4 equations. You gotta write down that there's a solution. Now, I don't care what lambda is. I care that there's a lambda. If I plugged in plus or minus 1 for z and that led to a contradiction, there would be no solution. So if you're claiming you have a solution, you must have checked every single one of those equations. Now we did. Okay. All right. So that gave me 2 points. I've got 0, 0, 1 and 0, 0, negative 1. Okay. Now that was subcase 1a where y was 0. Let's look at subcase 1, 2. 1b, where y isn't 0. So I'm still in case 1. We've looked at equation 1. Subcase 1b, y is not 0. Okay. Well, if y isn't 0, I'd be able to solve for lambda. Okay. So then from equation 2, I would get that lambda is equal to 1. Okay. Now, if I plug that into equation 3, that becomes negative 2z equals 2z. You might at first say that's not possible, but you would be wrong. Z could be 0. Okay. Because this means that 0 is equal to 4z, z is equal to 0. Okay. So I did get a solution here. Okay. So now, let's see, I checked equations 1, 2, and 3. Let's go to 4. So what do I know? I know that x is 0 and z is 0, but I've still got to solve for y. So I'm going to get 0 squared plus y squared plus 0 squared equals 1. Y squared is 1. Y is plus or minus 1. So I'd have 0, 1, 0, and 0, negative 1, 0. So that's case 1, which we had to break up into 2 subcases. These are long problems. I'm going to end the video here and continue the problem in the next video just to keep it from getting too long. I'm never quite sure what YouTube's limitations are.